So, hello again, YouTube. Uh, just real quick, I haven't made a video in a while, and that was because I started going to college. But in the meantime, I have found some time finally to work out some more time to build stuff. And that's exactly what we have here today. These are some logic circuits which I made. Uh, Specifically, this is a half adder made out of transistors. What it does is it adds two 1-bit binary numbers, so it basically can add up to the number 2. So that's fun. Also, I have here made out of 74 series logic, which is like these logic gates. You can see them, but they're on an integrated circuit. And this is a flip-flop circuit. It's not really fully made yet, it's just the memory part, but this is part of a computer memory circuit. It's if you could get a bunch of them together, it would be for a CPU register or SRAM, static memory. There's also DRAM, dynamic memory, and that uses capacitors instead of just storing it in a feedback loop of transistors, which this does right here. If you wanted to make one out of capacitors, it is a simpler circuit. Basically, you just have a transistor, and it turns on a capacitor, and then the capacitor fills up, and basically you have your bit stored. But of course, the capacitors, they drain really fast, so you have to keep refreshing it, and you need some circuitry for that, which I have not been able to build yet. So that's off the table for right now. So the whole idea behind this circuit is that I can, I guess, someday be able to build a fully functional computer. Probably going to be out of transistors or 74 series logic. 74 series logic. This would be easier to build, but transistors, I get to build it from the bare components, and I don't know. It'd just be more complete with transistors, because if I use logic gates, then I might be tempted to just buy, why am I going to make a flip-flop? Why don't I just buy a logic gate for a flip-flop? Why am I going to make a half adder circuit or a 4-bit adder circuit when I could just buy those online? And if I do it in transistors, I could just have everything in transistors. It's all at the same level of complexity, and I could just go from there. But of course, a concern about these transistors is that it's only a half adder, and I'm already using 8 transistors. For a full adder, that would require, well, 8 more, plus 2 more for an OR gate that will complete the full adder circuit. If you don't know what I'm talking about, this circuit right here is a full adder. Excuse me for the tripod. But yeah, so here I have it drawn out. You can find numerous descriptions of how to build these online. It's a very common logic circuit, just depending on how they are arranged with each other. You can see in green, this is a half adder. That's what I got over there. Yep, over there. That's a half adder too. So you could see it has 2 AND gates, a NAND gate, and an OR gate. And you can see that I built that on my version of the circuit. You can see you have 2 AND gates, a NAND gate, and an OR gate, but it's split up on 2 circuit boards. This kind of density is kind of a problem, since I calculated with the density that I have. If I make another half adder circuit, well, I'm already up to 4 boards. If I want to combine them together to make a full adder, that's up to 5 boards per circuit, and those boards can get expensive really quick. The transistors and resistors, they're not cheap, but the board is where the expense is at. The wire is also another concern, but I've managed to mitigate the expense with that. This is actually salvage wire from I believe it's a stereo system, and I can get more off of some computer cables, Ethernet cables, that kind of stuff. So that shouldn't be a problem. One helpful thing is always use colored wire. It makes wiring these circuits much easier, because before I used to use this kind of stuff. This is speaker wire. It's great. It comes in a spool. It's a big spool. It's solid core wire. You can just put it on there. But one of them is gold. Well, it's copper. And there's a transparent plastic coating. And one of them has a white stripe. Can you see it? No, you can't. That's my point. And nice thing about this colored wire is it's colored wire. It's thin, I guess, but it's hard to strip. And you have to use a soldering iron for that. I actually, thankfully, at the college which I go to, there's a workshop which I can go to, like a laboratory, that's open, I guess, for anyone to use, and that's what I do. Ignore the bad soldering joints. That's the next thing which we are going to talk about right here. When I had initially drawn up this circuit, this full adder circuit, I initially wanted to have it on a single board like this. You can see I could have a single board, and this board would, rather than having half of a half adder, so a quarter adder, no, it doesn't add a quarter, it's half of a half adder. Instead of doing that, I could have a full adder on an entire board. You can see this is a half adder, this is a half adder, and this is the OR gate that switches between them. And there's plenty of room for terminal connections, A input, B input, carry in, carry out, some as well, that's kind of important, 5 volts and ground. These are powered by 5 volts. It's transistor logic, not CMOS logic, which is 3.3 volts. That's what you get when you work with transistors. Very fun. So I thought I could do this kind of density, and turns out it is very much possible. I have a prototype of this density right here. You could see some of the differences is that I have the transistors, they are laid out next to each other. This is actually a NAND gate, and it's fine, I guess. The resistors are packed in tightly, much more tightly than it is here. As you can see on this board, it has a bunch of empty space in general. It's very inefficient. There's enough space for me to put labels on it, so you know that's inefficient. It would be good for display purposes, I guess, to show the individual gates and how they're working, such as on an educational model or some sort of that, but that is not what this is. I'm trying to build an actual computer here. I'm not trying to educate anyone other than myself, and that is really my point right now. And you can see that this logic gate right here, it looks fine, it probably is fine, probably would work, but the soldering is just bad. You can see here, like, and this is my fault, I haven't soldered in a very long time. I don't know if I'm using the right kind of solder. These boards are really cheap, once again, because I have to use so many of them, so I get the cheapest ones that I can get, and the terminals, they come off, these little copper pads, just come off, and I gotta cut these little wires from the resistor leads, the transistor leads. I gotta bend them. So with practice, I should be able to get up to this density, and this will save me numerous amounts of these circuit boards. So I'm not sure whether I would like to proceed with the design for an entire computer or something of the sort using this kind of density. This kind of density is very inefficient. But at this level with a half adder, you know, it's manageable. I could, 5 circuit boards for a full adder, that's manageable, especially I could stack them up on top of each other. It's like, I'm paying like $5 for the circuit boards. I found some cheaper ones on Amazon, so I got those. Of course, probably be of the same quality, but whatever, I can learn to deal with it. And I could stack them up on top of each other. I could probably make a 4-bit adder, and that would be maybe about 12 inches tall. You could see if I space these about an inch apart, and if I have 5 and 5, that's about 10 inches. So, and if I can increase the density that much, yeah, I could do it on a foot. I could have a 4-bit adder in a foot. 4-bit foot long, if you would say. That would be manageable. I am working on right now on making a 3D printed case for these circuit boards, so I could just slide them into a 3D printed case. It would increase the density. You can see I have wires going in between these circuits, so I could just stack them on top of each other. They could sandwich together like this, and then these wires, they could go up to the next circuit in much the same way, and that would be good right there. I could have a 4-bit adder circuit using this density at this level. I could get some more soldering practice, which I very much need at this moment, and that would be good. And of course, I could probably make a couple flip-flops using that kind of density as well. But to get any kind of real computing power, I gotta use this density. Or should at least try to. Maybe not this dense, but I kind of gotta approach something like this. That would be ideal. So, what my plan is, I guess, is to build some kind of 8-bit computer device. I'm studying computer architecture right now, and by studying, I mentioned earlier that I am in college. I'm not studying that in college. I am studying electrical engineering. I haven't really started engineering electric right now, which, electrical engineering does entail stuff like this. Especially if I get into computer engineering, which I am considering. But, I'm a freshman right now, so I'm basically just taking, your basic calculus or whatever. And that's fun and good. Maybe I could get a computer to do calculus, find the derivative or something of binary numbers, if that's a whole other thing to itself. But I've been reading this book from the library, Computer Architecture, Fundamentals and Principles of Computer Design. And you can see this book, it's a book about computer architecture in a very, I guess, general way. You can see it has the adder circuits, carry look-ahead adder. See, I'm still trying to understand what that is. My current design, I'm just going to do a ripple carry adder, which is basically you have your half adders and the full adders, they just flow into one another. Interesting enough, one way to save a couple boards is if you're building an adder of this way, you get one half adder. So you get one half adder and then the rest are full adders because they carry in from the half adder. And you need that carry input for a full adder circuit. That's why it's full. It's adding the carry input. Very good for that. And so that is the design for, I guess, some idea of what I could have a computer. I kind of have it visualized in my mind right now, but I need to actually write it on paper to make some better interpretations of what this thing would actually be. It would presumably be a transistor computer that can, I'm thinking 8-bit. That'd be swell. Of course, it'd have all these adder circuits. That's part of a computer circuit called the Arithmetic logic unit. I have numerous things written about this. You could see here's a diagram for an 8-bit full adder circuit. Why is it an 8-bit full adder when it's, of course, you'd use full adders. You wouldn't have an 8-bit half adder. But that's besides the point. You can see each one of these is a full adder. So each one of these is 5 of these boards. Whoa, pretty cool, bro. You can see I've simplified it vastly. This is, you get 5 volts, your ground, and then the carry input, and then power is like daisy chained in between them. Like you see how this is logic carries in between them, and power wires just carry in between them as well. So I could just have a string like this. Only one of the boards has a power input. That's good. They're all wired in parallel, and they will require vast amounts of amperage in 5 volts DC. You know what else requires that? Computer power supplies. So I'm good on that part, at least for that. I might have to convert 12 volts to that. Stepping up to level 2, we are on logic circuits. This is a 74181 ALU schematic. If you don't know, the 7410181 was a ALU, Arithmetic Logic Unit, released by Intel in the 70s. It was a precursor to microprocessors, and it's probably the simplest circuit you'll ever see made by Intel, and you could make this out of transistors. I believe this has 70 something logic gates, and it's 4 bits, so yeah. You can see this is a carry look ahead adder design, and this is a carry look ahead adder. A little too complex for me right now, so that's why we're going with the other design. Alright, here's what I wanted to get to, and forgot to with that little bit of distraction. But this is the design of computer architecture. There are multiple kinds of computer architectures. We could get into neural networks, which are complicated, and I don't know how that works. There's also register architectures, which use registers to compute. Again, that's a little bit more like the human mind, which doesn't separate a processor and memory, at least from what I'm concerned. I need to study more on that. But this is called a von Neumann architecture, and this is what basically all computers use. MacBook over there, this phone I'm recording on, this kind of stuff. Of course, there's variations. That's 64-bit, x86. This is RISC architecture, ARM CPU. But they all kind of go with the same design. There are also permutations on this design, even more. There's the Harvard architecture, which has separate memory units, but this is basically, they're all like this. So they have an arithmetic logic unit. That would be the 8-bit adder, which I have shown. So all of these circuits, 5 of these to 1-bit adder, and then you gotta have the rest of them for an 8-bit adder. And then if you want to have an adder subtractor, which you kind of do to have any kind of opcodes or anything, there you go. And of course, this isn't talking about Boolean operators, which presumably would just be a string of AND gates or NAND gates together. Would be simple to do, and I could just control everything using exclusive OR. I believe that's what works as a switch. Exclusive OR gates. Those exclusive OR gates, again, this is basically an exclusive OR gate, so more circuits just for fun. If I'm going with transistors, that's why this doesn't seem too bad right now, but yeah. So you have a control unit, an ALU, which is all those circuits, the adders, the Boolean operators, everything. That's just the ALU. And then there's a memory unit. That would be flip-flops like that thing over there, which I'm going to get to eventually. And then there's, of course, the control unit. What the control unit does is it controls data flow of the computer. This is where we get things like clock speeds. People are talking about overclocking their computer. And what the clock does is it controls the data flow on the bus. There's a bus of data. So it would be 8 bits if this were an 8-bit CPU. Right now there's nothing imagined with me. But it would control the flow of data between the ALU and the memory, roughly like that. And of course the control unit goes in like that. There's also an input and an output and that kind of stuff. And this is the control unit. This is probably the hardest part because it gives the opcode to the ALU and then it controls the bus. I kind of know how to build circuits that are in the ALU. Kind of know how to build circuits that are in the memory unit. SRAM units here, adders, that kind of thing here. I don't know what's here. There's more registers here, more logic gates, that kind of stuff. But I'm probably going to have to do a lot of custom design for this to have finally built my own CPU architecture, and that's just the CPU. We're not talking about RAM, we're not talking about even cache, we just have registers. And of course in an actual CPU they have, as I mentioned, the dynamic RAM is used in the RAM modules, like the actual RAM. And registers are made using the SRAM, the flip-flops and stuff. I'm gonna go all flip-flops and just have it have registers and won't really have RAM. And this could just be the computer, basically. I don't really have anything else. I could have I/O interfaces. That's a whole another can of Shrek, which I gotta get into. And then there's of course graphics. People are always talking about their graphics card. Oh, there's display. There's 4K monitors. Look at mine. I have the best display we got here. Have you ever seen that video which I made? Yeah, the one where I put a bunch of LEDs on a breadboard. Yeah, the one which got like 20 views. Yeah, that one. These are the LEDs, and it's 1, 2, 3, 4, 5, 6, 7, 8. So that's great for the 8 bits, and that will get me somewhere with that. That could be my display. It can show binary numbers just as it is, like that. If I want to show up data on something like a calculator display, then that's a whole another thing, and I have to build an analog, binary to decimal converter or something that could show up on the LEDs. I think it involves a bunch of diodes, but I'm not getting into that right now. And of course, that would require its own 3D printing case and more circuit boards. Fun. Now, for some I/O interfaces, as I mentioned, we're using flip-flops for RAM, and those will store data. You don't have to touch them; you just have to provide power to them, and that's great and all. But if we want to have hard data storage, like a hard disk, we're not going to have a hard disk because that's hard to do. Hard disk. And it's magnetic memory. You're spinning a magnetic disk. You're reading magnetic stuff with even more circuitry. So what we're doing is a punch card reader or punch tape. As you might have known, older computers that were programmed in this way, there would be a punch tape. It would go into a reading machine and it would read out the data. I kind of studied those a little bit. A lot of them had like pins that would go into the holes and see if there was a hole wherever there needed to be a hole. But I'm not going to do that because I have things called photoresistors, and that's what I'm going to use. So there's going to be something that emits something that scans something. So in practice, I'd have like an LED here. I don't need to have an LED for each one. I could just have a big LED bar right there. And numerous amounts of photoresistors, which can sense whenever something's happening. Photocell, LED in a photocell. They could sense whenever there is light flowing through easily, and that will trigger a transistor through a voltage divider. For the voltage divider, I'm going to have to find out which kind of resistors to use for that. That's just going to be calibrated based on how much light goes through the paper, and that's how we configure that. So that's a thing. And right, there's also logic gates such as these ICs. If I wanted to build something out of that, I would only use NAND gates, and that's where we get NAND only logic. A lot of computers, you can build an entire computer using only NAND gates, using only these. You don't even have to think about the transistors or anything. We're getting multiple kinds of ICs. You could just use these only. Using this thing, 7400. One of these is one of those. They all look the same though. It has 14 pins. Yeah, right. 4. It's quad NAND. Quad NAND. You see the little dots? That makes it NAND. If you goes like this, it's AND. If it has the little dots, it's NAND. Ooh, that's a good time right there. And of course, you have an AND gate and an inverter, so you can build an AND gate by shoving the outputs of an AND gate into a NAND gate built to be an inverter. You can do that too. Just leave this alone. You could also do an OR gate. If this will always be on, or this will always be on, so there you go. exclusive OR gate, and that's the whole thing with that. You wouldn't do this if you're building a computer using only transistors because, of course, you're wasting stuff here. You only need 2 transistors to build an AND gate. And of course, if you're doing this, you're using 4 and just wasting them because all this is doing is reversing the part of it, the not part of it, the not and part. And here we go with transistors. These are the circuits which I use. Slightly modified though. You can see these have 4.7 kilo ohm resistors connected to the ground lead, and they have 10K resistors going in between the A and B inputs. What I decided to do is simplify it by using only 4.7K resistors, and you see we have 1 on the power input and 2 on the A and B inputs. So we are using more resistors, but 4.7K times 2 is about 10K, or at least the transistors don't care. That's the advantage of digital logic. It's on or off. If it's really in between, this goes a little differently. It doesn't matter. That's why we use digital instead of ternary logic. And then there's all kinds of other stuff right now. So let's actually demonstrate this. I don't have a real power source right now to power these gates, but what I do have is an Arduino. And the whole thing with the Arduino that makes this so funny, I guess, is that the Arduino has a little circuit on it called the 18MEGA328. It's a microcontroller, you see right here, a microcontroller, and this is a much more powerful computer than anything I could ever build. And we're using it as a power supply because I'm cool. Because I watch anime and I'm a fun child for that. So when you turn this on, this is a flip-flop. It doesn't have the whole set reset thing. So it's kind of random whatever light turns on. But basically you have 2 inputs. And when you connect in the ground, I can do this on camera. No, I guess it's not that one. So yeah, you see, you touch it once, and then it switches all the way. And then you could do the same thing with the other one, and then it switches, and then you could just do it, like that. So it's always, so it doesn't matter if you're still pressing it. It remembers this. It's a memory circuit. And you could use this if you're trying to convert a momentary switch into a different kind of switch. Instead of an LED, you could plug this into another transistor, which would go into a relay. So there you go. That would be a logical application of something like this instead of building a computer out of it. And when you're making these drawings on this paper, it helps to have one of these. This is a logic maker thing. It just, you see this is, you see you got your little AND gates right here, and then your OR gates, and that's really all you need. You got your NOT gate and the circles to make it NOT. So that's where we are right here. Obviously, I'm still working on that robot which I'm building, but I can't really have it with me here because it's a big metal robot. And this is carpet, and Miku is over there. You see, here's Hatsune Miku, and Hatsune Miku does not like to have robots in the same room as her. I asked her, she said no. And that's really all I need to be convinced. So let me know what you think in the comment section. Is it a good idea to build a computer with logic circuits or whatever? Should I focus more on my robot? Will logic circuits help me build my robot? Should I just program the Arduino for the robot? Or should I build a microcontroller out of logic circuits and program it using paper tape? And that would be a whole another thing, another interesting challenge which I would have to meet. Completely unnecessary, and would just make my robot building procedure more complex. Also, for my humanoid robot, which I am still working on, I'm just working on it by doing research, and the way I do research is by doing other projects, including this and the robot. But I have bought this. This is a foam head. It's used to put wigs on it, but I'm trying to make a face for my robot. It's not really part of the whole robot part. If you want to know my skills as an electrical engineer, look there. It's not good, but I can do it. And that's my philosophy when it comes to all this other stuff as well. I'm trying to make a silicone face using this foam head. Try to model it off of that. So that's another thing which I'm not going to do because I have chemistry homework. Maybe I could learn some chemistry to do that. Not very much, so. Not very much. Here's my bag of interesting electronics. Here's another thing which I use. It's a voltage meter, and let me tell you, when you're measuring these transistor logic circuits, it's good to have one of these because, of course, as I mentioned, digital circuits, the transistor has a certain threshold to where it's either on or off. Usually it's 0.7 volts. And what I like to do is I spec out my resistors by using this. So if it's 5 volts, it's good. If it's not, it's off. And if it's somewhere in between, I can add or subtract more resistors and calibrate them using that. This is $4, by the way. You could use a multimeter too. I got one of those somewhere, but maybe I should use that. But I am going to have this mounted on my computer when I build it. It could be like all Dexter's laboratory stuff kind of going on here. I could feel like I'm a bad scientist instead of just, I just live here with Miku. But that's beside the point. Good night, America, and I will see you in another video. I've been absent for some time, but I hope I have made it up to you and more by providing you 32 minutes of wholesome entertainment for your family.